We are gathered here today to evaluate the 5 beastly integrals from the 2022 MIT Integration B finals. Why, you may ask? Well, I was bored, so here we go. Now, problem 1 shows an unhealthy obsession with trig identities. But thankfully, all we need is some basic trigonometry, plus a careful dissection of the problem here. So we're going to have to perform a bit of surgery here and pick out the parts of the integral and see what they actually simplify to. So first up, notice that we have to square these two bad boys, right? So on expanding the squares, we're going to get a squared sine of 20x plus a squared cosine of 20x, which gives us 1. We're also going to have a squared sine of 22x plus a squared cosine of 22, squared cosine of 22x, which again gives us 1. And notice the 3 here. So on expanding the square, we're going to get a 9 times the square of the sine of 21x, as well as the corresponding cosine term, which gives us 9 times 1, which is 9. So add up all the stuff and you get an 11 that I'm just going to write here on the side so I don't forget this later. And what about the cross terms? Well, the cross terms will give rise to 2 times sine 20x times sine 22x plus a cosine 20x times the cosine of 22x, as well as a 6 times the sine of 20x times sine 21x plus the cosine of 21x times the cosine of 20x. Alrighty then. And again, you have 6 times the sine of 21x times the sine of 22x and the corresponding product for the cosine as well. Okay, and all of these expressions can be simplified using the addition of angles formula for the cosine function. So we know that cosine x plus y can be expanded as, wait a second, we're going to need a minus sign here so that we get cosine x times cosine y plus sine x times sine y. So that means for the first expression here, you get 2 times the cosine of 20 minus 22, which is negative 2x. But again, the cosine is an even function, so you don't have to care about the negative sign. So you have 2 times cosine 2x. And for the second expression, we have 6 times the cosine of x. And the same thing for the third expression. And this simplifies our work quite a bit. So we can call the integral I. And this reduces to the square root, the integral of the square root of 11 plus 2 times the cosine of 2x, plus adding up the 6 times cosine x terms, we get 12 times the cosine of x, and we're integrating with respect to x, of course. And cosine 2x can be expanded using the double angle formula as 2 times the squared cosine of x minus 1. So we have the integral of the square root of multiplying out by 2. We have 4 times the squared cosine plus 12 times the cosine plus 11 minus 2, which is 9. And all that's left now is to complete the square. So you can write this as the integral of the square root of 2 times the cosine of x squared plus 2 times 2 cosine x times 3, which sits well with the 9 term here because it's the square of 3. Alrighty then. So we have the integral of the square root of the square of 2 times cosine x plus 3. And the square root cancel out pretty nicely, and we're left with the positive or negative integral of 3 plus 2 times the cosine of x dx, which evaluates out to 3x plus or minus, that is 3x plus 2 times sine x, plus a constant of integration c, and that wraps up problem 1. Now, problem 2 is something that can be solved using my favorite way to integrate, that is the Feynman way. So we're going to define an integral function I of some parameter t as the integral from 0 to infinity of e to the negative tx times the, terribly sorry about that, e to the negative tx times sine 3x divided by x dx. And we're going to differentiate the integral function with respect to the parameter t, and can we perform the switch up of the integration and the differentiation operators? Well, you have this damped exponential term here, which is pretty useful, defining t to be positive here, or at least non-negative. Yeah, non-negative would be quite helpful. So defining t to be non-negative, and we have this bounded sine function, and 1 by x is a decreasing function on the interval from 0 to infinity, right? So by Dirichlet's convergence theorem, the integral does converge. So yeah, we can perform the switch up, and we have the integral from 0 to infinity of, because of the switch up, the total derivative becomes a partial one. So it's a partial derivative with respect to t of e to the negative tx times sine 3x divided by x dx. Now, because we're differentiating partially with respect to t, the x terms are constant, so we have sine 3x by x times the derivative of this exponential term, which is just the repeated function, times the constant in the t world term x, negative x that is, and the x terms cancel out pretty nicely, so the derivative of I with respect to t equals the negative of the integral from 0 to infinity of e to the negative tx times the sine of 3x dx. And this can be evaluated pretty easily using either integration by parts, or you could invoke Euler's wonderful formula, which is, of course, something that I can't resist. So we know that e to the ix equals cosine x plus I times sine x, so all we have to do is replace x by 3x, and we see that the imaginary part of e to the 3ix equals the sine of 3x, right? And there's a negative sign here as well, and we know that the sine function is an odd function, so let's just pop in a negative sign here, so that we know that the imaginary part of e to the negative 3ix equals negative sine x. So yeah, that gets rid of one pesky negative sign for now, that is. So I prime of t equals the imaginary part of the integral from 0 to infinity of e to the negative tx times e to the negative 3ix dx, and multiply out the two exponential terms. You get a negative x times t plus 3 times I. Pretty easy to integrate. You have the imaginary part of, again, the repeated function e to the negative x times t plus 3I divided by the derivative of this argument, which is negative t plus 3 times I, and the limits are 0 and infinity. So let me just expand this term upstairs. We can write this as e to the negative tx times e to the 3ix, negative of that is. So in the limit as x approaches infinity, this damped exponential term approaches 0, and the entire thing collapses. So you're left with minus the limit of this thing as x approaches 0, which cancels out with this negative sign. So you need the imaginary part of plugging in the limit as t approaches 0, you have 1 times 1 in the numerator. So yeah, that's 1 over t plus 3 times I. So you need the imaginary part of this complex number here, which can be extracted if you just expand using the complex conjugate. So that's exactly what we're going to do. So we have the imaginary part of t minus 3 times I divided by t squared minus 9I squared, right? So that's a plus 9. And the imaginary part here sorts out to negative 3 divided by t squared plus 9. Okay, cool. So that's the derivative of I with respect to t. And we now plan to recover our integral function from this derivative. And for that, all we need is to integrate with respect to the parameter t. That is just the familiar arctangent structure. So we have this negative 3 as a constant term, and we have to divide by 3, and we have the antiderivative giving us the inverse tangent of t by 3 with the no limits. This is an indefinite integral, so we have a constant of integration. And on the left-hand side, we just have the function I of t. And now we have to figure out a way to calculate this constant of integration. Recall integral function, please. So I of t equal the integral from 0 to infinity of e to the negative tx times sine 3x divided by x dx. And remember when I said that t would be non-negative? Yeah, that helps. That helps quite a bit. Because if you plug in t being equal to 0, then you get e to the negative tx being 0, being 1, that is, e to the 0, which is 1. And you're left with this nice Dirichlet integral that on this limit evaluates out to pi by 2. And you could also use the limit of I of t as t approaches infinity, because that would have collapsed the integral function completely, and you can deal with this inverse tangent quite well. So yeah, there are two ways to evaluate it, but I'm choosing the one where we plug in t equal to 0. So I of 0 equals, inverse tangent of 0 is just 0. So I of 0 being equal to pi by 2 equals 0 plus c, that's c, and that is your constant of integration. So finally, we have I of t being equal to pi by 2 minus the inverse tangent of t by 3. And we were interested in the case of t being equal to 2, right? So this implies that I of 2, which is our target integral I, equals pi by 2 minus the inverse tangent of 2 by 3. And using a nice property of the inverse tangent function, where the inverse tangent of x plus the inverse tangent of the reciprocal of x equals pi by 2, provided that x is positive. So yeah, that means we can write inverse tangent of 1 by x as pi by 2 minus the inverse tangent of x. And just plugging in x equal to 2 by 3 here, this means that I of 2 equals inverse tangent of 3 by 2, which agrees with the answers provided by MIT. So yeah, we're cool. Problem 3 looks like something straight out of your trigonometric nightmares. Yeah, this really is something. So we're going to integrate it using the force. But I'm kind of, running low on the force, so we're just going to use the Dirichlet kernel. And there's a reason that these two fractions have been written in such a highlighted way, calling the integral I as always, so we have something to refer to. Anyway, there's a reason they're highlighted, because these are the perfect structures for using the Dirichlet kernel, which is a wonderful relation stating that the sine of n plus 1/2 of phi divided by the sine of phi by 2 equals 1 plus 2 times the sum over k from 1 to n of the cosine of k times phi. So let's work out what exactly here is phi and n. Well, you have sine 50x, right? So that means phi should be 100x, so that you get this sine 50x term down here. So replacing phi by 100x, so you can write this as 100kx. Alrighty then. And same thing over here. And if you have 100x over here and n plus 1/2 here, you can run through the math. You still need 100 over here. So you want n to be 100. And I can replace this n here by 100. All right. And what about the other fraction here? Well, this here is the sine of, you should have a 102x term, so that you have sine 51x down here. And again, and again, you would need n to be 100. Okay, and this equals 1 plus twice the sum over k equals 1 to 100 of the cosine of 102kx. And wait a second, we already have one sum over k, right? Multiplied by another sum, so we should change up the index variable. We should use j for this one. So yeah, this is much better, 102jx. And okay, this looks extremely cool. No doubt, this looks extremely cool until you actually, plug in and multiply terms and integrate. Nah, I'm just kidding. It's actually pretty simple. So this implies that I equals the integral from 0 to pi, or 2 pi? It's 2 pi. The integral from 0 to 2 pi of the cosine of 2022x times 1 plus the sum over k from 1 to 100 of cosine of 100kx. Terribly sorry about that. So cosine 100kx. Plus, no, wait, the two fractions were being multiplied. So multiplied by 1 plus the sum over j from 1 to 100 of the cosine of 102jx. Okay, cool. Although this looks daunting, you actually have some pretty satisfying results popping up here. So you have the integral from 0 to 2 pi of a lot of stuff, and one of that stuff is the cosine of 2022x. Okay, And if you integrate the cosine of 2022 x from 0 to 2 pi, you're going to get a sine of 2022 x divided by 2022 x. So just plug in 0 or 2 pi, you're going to get 0 anyway. So let's just ignore this term here because it evaluates out to 0. And you have this sum over k from 1 to 100 of this cosine 2022 x times the cosine of 100kx plus multiplying it out forward, you're going to get a 1 times all of that stuff is going to give you, wait, I'm kind of mixing, nope, I'm not mixing it up whatsoever. The sum over j now from 1 to 100 of cosine 2022x times cosine 102jx. And you're also going to have this double sum here over k and j both running from 1 to 100 of cosine 2022x. So, okay. And wait, these coefficients of 2 that I forgot. Not cool whatsoever. All right. So you can write this as 2 times this, and 2 times 2 is 4. All right. Cosine 100kx times cosine 102jx. And let me just close this, close the big old braces we have here. Okay, now once again, we need a careful dissection of the problem. This is the product of cosines. If you use those product of sum formulae from trigonometry, then this product of cosines results in a difference of cosines. And the arguments of those two cosines are going to be even integer multiples, right? They're going to be even integer multiples of x. Okay, so once again, if you integrate those, you're going to get sines of even integer multiple of x. And if you integrate from 0 to 2 pi, you're going to get zeros again. So both of these sums just crash down to 0, which is pretty damn cool. Now that was awesome. That simplified our work quite a bit. But we still have to deal with the integral from 0 to 2 pi, 4 times this integral, that is, of the double sum over j and k from 1 to 100 of cosine 2022x times cosine 100kx times cosine 102jx, integration with respect to x. Okay, now what? Well, we could expand using those product of sum formulae again, but I love using complex numbers whenever I can, so that's exactly what we're going to do. So you can switch up the order of the integration and the summation operators because obviously what we have is convergent. So we have 4 times the double sum over j and k of the integral from 0 to 2 pi. Now, how exactly do we define the cosine function in complex analysis? Well, it's defined as e to the argument, that is 2022x times I. So that's 2022ix plus e to the negative 2022ix divided by 2 times this e to the 100kx plus e to the negative 100kix, forgot the I, the most important ingredient, the imaginary unit, divided by 2. And I've run out of writing space, so let me just make some adjustment over here regarding space. So we have, we're left with e to the 102jix plus e to the negative 102jix divided by 2, integration with respect to x. And now we have to multiply out these terms. And you can notice some really nice patterns over here. I mean, you don't even have to perform all the manual multiplication. I mean, just looking at it tells you that, okay, the denominator is going to be 8, right? So let's just get rid of this. If the denominator is 8, so that cancels out the 4 pretty nicely, and we have 1/2 outside. Okay, cool. And just looking at the terms being multiplied, you can decipher that you're going to have an e to the 2022 plus 100k plus 102j, factoring out an ix, and you're also going to have a plus e to the negative of all of this stuff. I'm pretty sure that's clear to everyone watching, so that I don't have to perform the manual labor, so you can do that if you want. Anyway, so we're going to have this term. Because of all the terms included, you're going to multiply everything out, right? So you're going to get pretty much every possible combination with the plus and minus signs. And this is equal to twice the cosine of this terrible argument that I'll write out later. I'll write this out later, okay? I will, because I have to integrate it. I have to integrate the expression in this color, whatever this color is called, I forgot. Anyway, so we have to integrate this, and I'm going to have to write it out, so yeah, be patient. So we're going to have this term with the 2022, 100K, and 102 being added, but we can also have them, we're also going to have them with alternating signs, right? And all of them are going to be 2 times cosines. So factoring out the 2, that means we have 2 by 2 outside, which cancels out pretty nicely, and we're left with the double sum over j and k of the integral from 0 to 2 pi of, I'm going to need a couple of big braces, 2 times the cosine of 2022 plus 100k plus 102j x plus, wait a second, I factored out the 2 already, plus the cosine of the other combination is 2022 plus 100 minus 102, right? X. And one more would be the cosine of 2022 minus 100 minus 102 x, and there's still one left. Yeah, I should have a cosine of 2022 minus the 100k. Forgot to write the index variables and all of this chaos. Really sorry about that, guys. My bad. Anyway, so you got 100k plus 102jx. Yeah, that should do it. Indeed, it should. And again, a careful analysis of all the terms involved. You have 4 cosine terms, and 2022 plus 100k plus 102j is going to be some even integer, right? So integrate this, you're going to get a 0. If you integrate from 0 to 2 pi, that is. So yeah, just scratch this, get rid of it. We don't need it. And what about the other terms? The other terms are pretty interesting because they have some negative term in the mix as well. You got this negative 102 or negative 100k, or both of the k and j terms being negative as well. So there are combinations of integers for j and k from 1 to 100 where these arguments all just cancel out to 0. That means you have the cosine of 0, which is 1. And you can test those combinations out as well, and you will get one term each. You will get one term each for every, you will get one combination of j and k each for these 3 cosine terms. So you have all that's left from all of the chaos of j and k is the integral from 0 to 2 pi of 1 plus 1 plus 1 dx, which is 6 times pi, which again agrees with the answers provided by MIT. And I think it would be nice if the viewer also investigates the zeros of the argument as I did before when I solved it. So yeah, not exactly very fun, but it's kind of cool if you think about it. It is kind of cool. Problem 3 is, once again, something back on my turf at least. So it's the integral from 0 to 1 of x to the 1/3 times 1 minus x to the 2/3. And this is just one of the 3 representations of the beta function. So the beta function with complex arguments m and n is defined as the integral from 0 to 1 of x to the m minus 1 times 1 minus x to the n minus 1 dx. So m minus 1 is equal to 1 by 3, right? So this implies that m equals 4/3. And by similar token, if n minus 1 is 2/3, then this implies that n equals 5/3. So your target integral I is just the beta function evaluated at 4 by 3 and 5 by 3. And it has a really nice relation with the gamma function, which we always invoke. I mean, that's pretty much the only reason we invoke the beta function in the first place. So we have gamma 4 by 3 times gamma 5 by 3 divided by gamma 4 plus 5 by 3 would be 9 by 3, which is 3. Okay, so we have gamma 3 downstairs, and this here is just 2 factorial, which is 2. So that means we have a 2 over here. And gamma 4 by 3, gamma 4 by 3. So this here is gamma 1 plus 1 by 3, right? So invoking the recursion formula for the gamma function, we're going to have 1/3 times gamma 1/3 times gamma 5 by 3. Now, what exactly is 5 by 3? Well, 5 by 3 is 1. 5 by 3 is 1 plus 2 by 3, right? So again, we can write this as 2 by 3 times gamma 2 by 3. So 2 by 3 times gamma 2 by 3. Everything is being divided by 2. So you got 2 by 9 divided by 2, which results in it 1 by 9. And you're left with gamma 1/3 times gamma 2/3, which is just 1 minus 1/3. And now for the wonderful reflection formula, that is going to give you pi times the cosecant of pi by 3. And that evaluates to, if my memory serves right, 2 divided by the square root of 3. So you have 2 pi divided by 9 times the square root of 3. And we're home free. That was pretty easy. Problem 5 is the hardest integral I have ever solved, and I am not joking. And this isn't even much of an integration problem, as it is a floor function problem. So yeah, just scratch that part of being a tough integral. The integral inside is pretty trivial, but the problem is you want to take the logarithm, the base 10 logarithm, or the common logarithm as it's called. You want to take the common logarithm of the answer, and then you want the floor function of it. So you want the integer part of that number. And this is just messed up. This is just messed up. So the strategy here is pretty unconventional in comparison to, everything else that we do here on the channel. It involves looking for upper and lower bounds for this beast that I'm just going to call I, even if it isn't really it isn't a pure integration problem, but we're still going to call it I. So yeah, we're going to call it I, and we're looking for upper and lower bounds for I. And the first step in all of the chaos that's about to follow is defining an integral I sub 1 as the integral from 2022 to infinity of 10 to the negative x cubed dx. And just for convenience later, I'm going to factor out, or I'm just going to expand, that is, I'm going to expand using 0 in the argument of the exponent over here. So the 0 that I'm going to use here is the cube of 2022. That is messed up, but just look at the integral. Did you seriously expect it not to be messed up? Like, seriously, bro? So you can factor out a 10 to the negative 2022 cubed here, and you can write this as the integral from 2022 to infinity. Sorry about that. Of 10 to the 2022 cubed minus x cubed dx. So that's I sub 1, and now we need to make some analyses using linearizations. And there are 2 functions I want to consider. One of them is the cube of x. So there's this function f of x equals x cubed, and this is what it looks like for non-negative values of x. So this is what it looks like. So wait a second. Slightly better. So the thing is, it's concave up. It's concave up and increasing. This means it has a neat property that if you define the linearization by drawing a tangent line at some point here, then the curve is always going to be above the tangent line. The curve is always going to be above the tangent line. In other words, f of x is going to be greater than its linearization. And we define the linearization as the equation of the tangent, right? Close to the point where we evaluate the tangent anyway, but we're not interested in that right now. So how exactly do we figure out the linearization? As I said, we just look for the equation of the tangent. So for that, we need the derivative of f with respect to x, which is 3x squared. And we're going to evaluate the derivative, or we're going to look for the linearization around x equals 2022. Because we're highly punctual, of course, solving the 2022 integration B 1 year after it occurred, but I already solved the 2023 integration B, so, you know, what the hell. Anyway, so the linearization of x around this point, x equals 2022, equals f of 2022 plus the derivative of f at 2022 times x minus 2022. Alrighty then. So f of 2022 would be 2022 cubed plus f prime would be 3 times 2022 squared times x minus 2022. So that's the linearization, and because the function f of x is greater than or equal to the linearization, so we're just going to write this expression in that manner, and f of x was in fact x cubed. So now for some magic. Negative signs means that you have to reverse the inequality here. Raising it to 10 doesn't hurt the inequality. Alrighty then. And integrating this positive function, these positive functions anyway, over a positive interval from 2022 to infinity doesn't hurt the inequality either. Alright. And if you multiply this inequality by a positive number that is 10 to the negative 2022 cubed, then you get the integral from 2022 to infinity of 10 to the 2022 cubed minus x cubed being less than or equal to the integral from 2022 to infinity of 10 to the negative of 3 times 2022 squared times x minus 2022. And all we need now is to multiply by another positive number that is 10 to the 2022 cubed. That is the negative of it, because that will give you the structure of I sub 1. So we know that I sub 1 is less than or equal to 10 to the negative 2022 cubed times the integral from 2022 to infinity of 10 to the negative 3 times 2022 squared times x minus 2022 dx. And if you just perform a substitution where you let x minus 2022 equal to t, this implies that I sub 1 is less than or equal to 10 to the negative 2022 cubed times the integral from 0 to infinity now of 10 to the negative, this horrible term that I keep repeating, times t dt. And the integration is pretty trivial over here. You're just going to be left with 10 to the negative 2022 cubed divided by 3 times 2022 squared. Terribly sorry about that, times log 10. Alrighty then, so that's an upper bound for I sub 1, and now all we need is a lower bound. Now that you have an upper limit, we're now looking for a lower limit. And for that, I'm going to analyze a different function. We're going to define f of x to be 10 to the 2022 cubed minus x cubed. Now this here is an exponential function with a graph that looks like this. This is what the curve looks like. So once again, we have an upward concavity. Means that f of x is going to be greater than the linearization constructed in and around some point, which you guessed it is going to be x equal to 2022. So for the linearization, I'm going to need the derivative here. So f prime equals the repeated function times log 10, and because of the chain rule, you're going to have a negative 3x squared here. So the derivative at 2022 equals, this term gives you a 1, and you're left with negative 3 times 2022 squared times log 10. And f of 2022 is conveniently 10 to the 0, which is 1. So the linearization sorts out to L of x being equal to 1 minus 3 times 2022 squared times log 10, all times x minus 2022. Okay, cool. And notice that the linearization is a straight line of negative slope, right? So that means at some point it could cross the x-axis and become negative. But the integral of our function f of x from 2022 to infinity is positive. So we're not interested in the part of the linearization that is negative. We'll only need the part that's positive. So L of x being greater than 0 implies that x minus 2022 should be less than, right? It should be less than 1 divided by 3 times 2022 squared times log 10. Okay, cool. So that means x is going to be less than 2022 plus this thing. And because f of x is greater than the linearization of x, the integral from 2022 to infinity is going to be greater than the integral from 2022 to infinity, which is greater than the integral from 2022 to 2022 plus this term here, 3 times 2022 squared times log 10, discarding the negative part. And now to evaluate this integral, so we have to integrate from 2022 to this thing here that I'm quite tired of speaking and writing as well. It's popped up a lot during this video. Anyway, so the linearization was 1 minus 3 times 2022 squared times log 10 times x minus 2022, and you have this dx as well. And you know what, you guys can just work out the integration. It's pretty trivial, right? But I'm not going to go through those manual calculations right now. Anyway, so this implies that f of x, the integral of f of x from 2022 to infinity, which equals the integral from 2022 to infinity of 10 to the 2022 cubed minus x cubed. And all you have to do is multiply this thing by 10 to the negative 2022 cubed, and we'll recover our integral I sub 1, correct? Where did it go? Yeah, right up here. So then we'll recover the integral I sub 1. So let me just scroll back down. Okay, cool. Yeah, there we are. So just multiply all the terms, and this implies that I sub 1 is going to be greater than or equal to the results of integration, and multiplied by this term gives you, there was a 1 in the numerator, so 10 to the negative 2022 cubed divided by 3 times 2022 squared times log 10, all multiplied by 1/2. So we can just write this as 6 times this term. Okay, cool. So now we have upper and lower bounds for our integral I sub 1. All that's left is to combine these two inequalities. So we have I sub 1, and if we multiply everything out by 10 to the 2022 cubed, that'll help out later when we take the logarithm using base 10. So we have 10 to the 2022 cubed here being less than or equal to the reciprocal of 3 times 2022 squared times log 10. And this integral I sub 1 times this constant is greater than 1 by 6 times 2022 squared times the logarithm of 10. And let me see. Yeah, that's a square. Okay, cool. Okay, now what? Now I need some idea of what order this amounts to. And I'm going to figure that out using the fact that the natural logarithm of 10 is less than 5 by 2 or 2.5 and is greater than 2. Alrighty then. So let me figure out the order of this term here. So 1 by 6 times 2022 squared times log 10. And because we're dealing with reciprocals, that means the signs of the inequalities are reversed. So this is going to be greater than 6 times, replace 2022 by 3000. So 3000 squared is 9 times 10 to the 6th power times 5 by 2. Okay, cool. So you have some nice cancellation taking place here, and you're left with a 15 term. So this is 15 times 9 times 10 to the 6th power, and 15 times 9 is a 3-digit number. So hopping the decimal point over there. Yeah, this is of the order of 1 by 10 to the 8th power, or of the order of 10 to the negative 8. Okay, cool. And what about the upper bound? Well, the upper bound we replace 2022 by 2000, right? So we have 3 times 8 times 10 to the 6th power, and replace log 10 by 2. Okay, cool. So we have 6 times 8, which is 48, 2-digit number. So this is of the order of 10 to the negative 7. So all of this implies that 10 to the negative 8 is less than 2022. Sorry about that. It's 10 to the 2022 cubed times I sub 1, which is less than 10 to the negative 7. Okay, cool. And now using the common logarithm, we have negative 8 being less than, this is going to sort out to 2022 cubed plus log base 10 of I sub 1, which is exactly what our target was. But of course, we still have to take the floor function, and this is less than negative 7. Awesome. So this implies that log base 10 of the integral from 2022 to infinity of 10 to the negative x cubed dx is less than 2022 cubed minus 7 and greater than 2022 cubed, negative 2022 cubed minus 8. So using the floor function, this implies that the floor of the logarithm of your integral that I'm not writing out again equals negative 2022 cubed minus 8. So that was one hell of a ride. And that was certainly a lot of stuff to write. I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.